Great. Thank you, Nadine. Yeah, it was a great pleasure today to be hosting Simone van Gaal, who is Associate Professor at the Brain and Cognition Department of the University of Amsterdam. He's head of the Conscious Brain Lab that he runs together with Johannes Fahrenfeld and Timo Stein. And the lab is studying the neural correlates of consciousness and the role of consciousness in cognitive control and decision making. They use various imaging techniques, including EEG, functional MRI, MEG, and so on. Simone gained his PhD from the University of Amsterdam, then spent some years as a postdoc with Stan de Hen before returning to Amsterdam to start his own group. Simone and I have known each other for many years. He's got lots of experience in the field of consciousness science. I think he's got a very healthy attitude to all the debates around theories and so on, and he just puts a premium on doing excellent science, which is what you'll see in the talk today. And looking back at the history of talks, I realized that Simone, you were actually one of our very first Consciousness Club speakers
Yeah, I remember.
in the pre-COVID in-person days.
Yeah.
So he's now coming back to tell us what you've been up to in the past few years. Take it away. Floor is yours.
Okay. Thanks, Steve, for the introduction. That was very nice. Let's see. Let's start sharing my screen. So this should work, right? You see my screen? Okay. So
Yes, we do.
I have to look away from the camera a little bit because my organization of my screen. So if I'm not facing you, then okay, that's because of it. So I decided to, so the title of the talk of today was what I proposed was linking global state fluctuations and recurrent processing to conscious perception in humans. And while making this talk, I realized that that was actually slightly too ambitious time-wise. So I'm actually mostly focused on the second part of the question. But I will still give you a little bit of a flavor of the first part. So you should not be too disappointed. But if you're mainly interested in the first part, then yeah, then email me or ask me questions at some other time. So basically, let's do that. So if you think about consciousness, what you usually see is this kind of very typical graph that everyone by now sort of knows in the field, where you have two axes, one representing the level of consciousness, or let's say the vigilance, wakefulness, or arousal. I especially like this figure because it's so clear that also that axis is very ill-defined. So it has, at least in this figure, four different words on the y-axis, all of sort of trying to mean the same thing. But at least, so what we know, there's fluctuations in this arousal state, which correlate with fluctuations in perceptual states or in the content of consciousness. And for example, just to illustrate here on the left, you see all these typical figures. We're saying if we are aroused and aware, we are like usually it's our normal conscious state that we're in right now. If you're in a coma, you're not aroused, you're not aware. If you're vegetative, you are aroused, but you're not aware, etc. So there's all these kinds of combinations of these two axes that give you in a certain state. But over the years, I think, although this is very generally accepted, there's not much work trying to link these things directly. So doing actual science, like to see how vigilance or wakefulness or arousal affects the content of consciousness. And that's what we tried to do over the years, and we did. So we basically tried to understand perceptual variability. So here's my version of this figure that I've just illustrated, where arousal just fluctuates sort of through the day, even now. And then we're testing like how do these arousal fluctuations then impact your performance? And we can do this, as you know, with various tests there, where you have a stimulus at threshold that's very difficult to perceive. And if you do these tasks in a lab, you'll see that people will sometimes see a stimulus or hear a stimulus and sometimes not. And we believe these seeing or not seeing is related to fluctuations in the state, right, in arousal. So over the years, this is the part that I'm not going to talk about more than this. We sort of did quite a few studies where we showed that if you look at pupil size as a metric of arousal, so there's many papers out there these days showing that pupil size is a very good proxy of certain neuromodulators in the brain, for example, noradrenaline, but also acetylcholine and many others, in fact. If you look at the state of, or the size of the pupil as a metric of the state of arousal of a subject before a stimulus appears, you see that there's this inverted U-shaped relationship between the arousal state and the likelihood that you're going to perceive that stimulus. And that's we did over the years in several types of experiments, and we tried to link that to all the neuromodulators that are involved using pharmacology, etc. But also we link this phenomenon to attention and metacognition and evidence accumulation, decision bias, etc. And some of the papers are listed here on the slide and the people that were involved. And this is it regarding this topic, basically. So it's more like a teaser. If you like that stuff, have a look and ask me questions later. So I'm just checking, Steve, are people, is it okay to ask questions during the talk, or what do you usually do?
Yeah, if the people have clarification questions, then I
Then that's
think
fine.
that
Okay,
would, but it's we normally try and leave the more extensive discussion
okay,
till the
good.
end.
Okay, I'm fine with that. So so let's not then, for the rest of the talk, I will make us mainly focus on this axis, right, which is the content of consciousness, uh, visual awareness mostly. So as you all know, and I've seen the people that joined this meeting, and many of the people involved know very well, there are many theories of conscious experience. Over 100, there's this website, I forgot the name, that now got launched very recently with all the different flavors of the theories. But what we did as a start is we did a survey uh, during the ASSC, during 2 consecutive years of the ASSC, the Conference on Consciousness, if I remember correctly, in 2018 and 2019. And there's one question in that survey that was about which theoretical position with respect to consciousness do you find promising? And as you can see, there's several theories listed here. And I'll just briefly highlight that I believe, at least, that the top 5 theories, at least in this list, have quite some commonalities. I know also, obviously, differences, which are usually talked about in the field. But I'd like to focus a bit more on the commonalities that these theories have, and then introduce the studies that I've done to test certain hypotheses of these different theories. And sort of brushing over the details and also ignoring other important parts of specific theories, which you can all find in these very excellent review papers that you've seen along the way, and there are actually many these days, many review papers on these topics. So I focus on these 5 theories, and if you like I said, brush over the differences, most of the theories sort of give a prominent role of, let's say, feedback, recurrent interactions, top-down processing as a sort of general category of neural responses. So this is obviously a bit more of a global workspace / local recurrency type of figure that you see here. But also like information integration has aspects of integration through feedback dynamics, etc., ignoring stuff about phi, etc., but just the general idea of perceptual integration. So let's say I would say a little bit as a caricature of how information is processed in the brain and reaches consciousness. Many people believe that you have some kind of background conditions, which we measured, for example, through pupil size. That's one of the background conditions that you can think of, like arousal states. Then there is unconscious processing of certain features, etc. Then there's some kind of magic going on in the brain, which is the true cause of consciousness. Let me state that I don't believe in that magic, but I'll explain later why I don't believe in that magic. And then there are some kinds of consequences that arise when you become conscious, and in an experiment you give a response, of course. And all these things are mixed when you do a task with a subject, right? It's difficult to disentangle all these different kinds of processes. So as a sort of simpler version of that, there's unconscious processing, which is mainly feed forward. Then there's some kind of starting to, like the start of recurrent interactions. There's some kind of integration between different features, which some theories like global workspace call pre-conscious. Other theories like local recurrency theory calls phenomenally conscious. Again, I'm not going to settle that debate here, but that's this sort of second state. And then there's conscious access would happen when there's global ignition, frontal parietal interactions, etc. So this is nothing new for any of you. The last stage, I think there's not much disagreement about. So um, I've done a lot of unconscious processing work in the past. So recently I did some studies with Timo, which I'm also aware of all the difficulties of studying unconscious perception, of course, and how to test whether stimuli are aware or not, whether you should do post hoc sorting or not, how you do the best task, etc., etc. This is just one study to highlight that we tried to do very recently, to have a very high-powered study in which we try to get objective invisibility. So it's basically D prime is zero of masked stimuli. Um, and we show that you still get all these, for example, very high or relatively high level activations in LOC and FFA, etc., to faces versus houses. Okay, so then what I like to do is a bit like ask the question, what's all the fuzz about? Like, why always this feedback stuff? Why is this all about feedback? What does feedback do? It's a very general thing. It happens all the time. I cannot be the neural correlate of consciousness. I think it would be strange to have such a general mechanism to be the neural correlate of consciousness. I also don't think in the end that we can find the neural correlate of consciousness. But let's just start with why do we talk about feedback in the first place? And to do that, I'd like to highlight a bit of work from my PhD supervisor. And why I would like to do that is because I'd like to give him some credit for the work that he did along the years, because he is retiring today. So Victor Lama is retiring. We have his final sort of goodbye ceremony at 4 o'clock today. We reveal his every professor sort of gets like a painting. So you're allowed to make a painting of yourself. Your painting gets hung up in some room where all the professors are. That will happen today. Victor will be gone. And I think knowing Victor, he won't be so involved anymore. So just so you know. But because of that, I thought it was nice to sort of highlight a little bit of his work, and especially his early work. So not the stuff about phenomenal consciousness and why you have consciousness when you can't report, etc. Not that stuff, but more the basic fundamental work that he did in the 90s and the 2000s, because I think some of you may not be aware, especially the younger crowd may not be aware of that work. So obviously Victor says feedback is consciousness. I tell you why. We've solved the mystery and I can retire today, right? So just to remind you, so this work all started with the concept, of course, of two different streams in the brain that are where information is processed through feed forward here in black arrows and feedback connections. We're mostly talking about the ventral root in this case. And the phenomenon that if you go further and further in the cortical hierarchy, the receptive fields of these visual neurons become bigger and bigger, of course, right? So the part of the visual field that these neurons look at is much bigger in temporal cortex, in ventral temporal cortex, LOC, whatever, than in V1, of course, right? So the part of the world that higher level neurons respond to gets bigger and bigger. So that's just important because in the early 90s and early 2000s, Victor and colleagues, for example, with Peter Roelsma and Hans Super, they did all these experiments where they showed monkeys patterns. So here on the right, you see just a homogeneous pattern of just one orientation. And here in black, this little circle do you see my mouse? Yeah. So the little circle here, it reflects the receptive field of a V1 neuron. So this is to illustrate here this little circle. The V1 neuron that we measure looks at this little piece of the world and sees an oriented line towards the left. In the left figure, this same neuron also sees the exact same information because the receptive field is small and the neuron just sees the exact same information. But we know that neuron looks at something that is more like an object, or at least there's sort of a figure that sits on a background, right? The background has different orientation than the foreground. So that's a more interesting stimulus, but initially this V1 neuron doesn't know because it doesn't have access to that information. So when you measure neurons in V1, you see that the first initial response is very similar for these two conditions. So here you see the response for these two conditions. And only later, here in this highlighted in this yellow part, you see that the response to the left figure becomes sustained much more than the response to the right figure. So I think most of you know this. This is called contextual modulation. And the idea is that visual regions higher up in the cortical hierarchy with larger receptive fields send information back to V1 saying, hey, this is interesting. This is an object, and let's start firing a bit longer. Why is it feedback? They did all these kinds of experiments where they lesion certain parts of the cortical hierarchy here illustrated with these more sort of darkish regions. So if you lesion these regions in the monkey and you do the same experiment, you see that the feed-forward responses remain relatively the same. So here in this lesioned version, but the feedback responses are strongly diminished, right? So the idea is, okay, there can still be a feed-forward sweep, information gets processed in V1, gets sent forward, but that doesn't reach anything here because these regions are lesions, so they can't send information back to modulate the early responses. So it's clearly feedback. And then a bit more interesting, I think, for the consciousness crowd, they did quite a few studies where they sort of either manipulated the state of the animal by giving anesthesia or by manipulating the likelihood that the animal sees that figure on a background. So let's start with the easy part, which is on the right. So in awake monkeys, you get the typical response. In anesthetized monkeys, so they anesthetize a monkey, open the eyes of the monkey, and still present the same stimuli over and over again. And you see that these cells in V1 are still feature selective. They still respond to the orientations that are presented, but the feedback or the contextual modulations is completely abolished. So anesthetized monkeys do not show this feedback response, do not have contextual modulation because there's a figure on one of the stimulus and not on the other. So then they did another experiment where they presented these figures at sort of unexpected locations. So the monkey fixates in the middle, and this square can happen at several locations throughout the visual field, and the monkey doesn't know. And there's lots of sort of jitter and other, the task is made a bit more complicated. And the monkey fixates in the middle, the stimulus is presented. If the monkey sees the stimulus, it makes an eye movement to the location of that stimulus. So you know the monkey has seen the stimulus and also reports the stimulus. But sometimes, or actually quite often, the monkey keeps fixating, although there is a figure presented in one of the corners of the visual field. So what you see is then when the monkey doesn't make this eye movement, so it doesn't report, I see a figure, you don't see this contextual modulation, which you see here on the right. So these are not seen trials, and these are seen trials. If the monkey sees the stimulus, you get this contextual modulation. If it doesn't see the stimulus, then you don't. So that sort of nicely illustrates, okay, at least these late responses in V1 relate to states of consciousness on the right and also contents of consciousness on the left. It's a very narrow window into the brain, of course. So it's V1. We don't know whether this is some kind of consequences of some other stuff that happened in between, right? It could be that there's feed-forward sweep, goes to, I don't know, fancy prefrontal cortex. There's the magic happening there. And that's what we're interested in. And then the information is sent back to V1, and then it's just some correlation of that magic that happens somewhere else. So we don't know whether this is the true thing that we're after, but it's a very clear and strong response that we see. Good. I just want to remind you that there's not only feed forward and feedback connections, obviously in the visual system, there's also lots of horizontal connections illustrated here nicely in a paper by Peter Roelsma from 2023. So you see here, on the left, you see the feed forward sweep going from V1 to higher up, anterior inferior temporal cortex. And here you see recurrent processing, which is usually thought of as a combination of both lateral and feedback processes. So you see feedback here illustrated with these green arrows between different regions, but you also have lateral connections within certain regions. And yeah, you know that these lateral connections are also used for grouping, for segmentation, etc. Right? So the combination of these two, so it's not only feed forward and feedback. This becomes important for the studies that I'm going to present later. Okay, good. So let's get to some data and experiments. So there's several reasons why you don't see or report something that I've just tried to highlight. You're either out, right? You're in a coma, you're on anesthesia, or you're sleeping. You have brain damage, haven't shown that, but you have like blindsight or anything. And models show that there's something about the input. So the input is not strong enough, or there's something about attention. So you have inattentional blindness or gorillas that you don't see, etc. So these ideas have led to these types of models. Um, this is a picture from Standahan and his group and his colleagues, but there's a very similar picture. If you look at the same time, the Tick's papers by Victor Lammert is virtually identical. The way they interpret the different boxes may be different, but the content of these four boxes is identical. And I'd like to go over these boxes a little bit because I'm going to present a study that directly tests this idea. And then later, we're going to do pharmacological manipulations. So first we test this model, then we do pharmacological manipulations to see what are the crucial mechanisms that drive conscious experience. And then, I take it from there, but that's the goal. So you have this 2 by 2 matrix where you have attention that's present or absent, and you have the strength of the input that's strong, that's either weak or strong, and weak can also be interrupted, so it could be masked, right? The input is strong, but because you mask it, it's strongly interrupted. And you get this feed-forward sweep for weak or interrupted stimuli on the top. When the input is sufficiently strong here on the bottom so that you can become aware of the information, in some of these models, you do not become aware because your attention is diverted somewhere else, right? You have inattentional blindness, attentional blink, so stuff like that. So you get, the idea is that you get these recurrent interactions, but it doesn't lift over the threshold to conscious access in a way because attention is lacking. And only in this right lower box, you have conscious access. There's strong stimulus response. The stimulus is strong. You have attention. You get global ignition, etc. Blah blah blah. You know all this. So I like this model. It's actually already 20 years old. So, but we still set out to test it in a proper way. And I'm going to say why I still think it's necessary to test it. And that's because I think the way this model, at least in that time, has been derived is a bit based on data that is not optimal for separating these 4 different stages. And I think one of them is the performance confound. And that's if you want to compare what happens during masking and what happens during attentional manipulations, such as the inattentional blindness, you need to sort of put them at equal footing. And what usually happens is that with masking, you mask a stimulus to death, you don't see it, you have D prime of 0, etc., and you only find a deep feed forward sweep. And then I'm generalizing a little bit here, of course, but we do attentional experiments, and we have some kind of cue that tells you where to look in the case of spatial attention, or we do attentional blink, etc. But we don't miss all the stimuli, but we miss some of them. So the stimulus is quite strong. We miss some of them. We select those that we do not attend, and then we say, hey, that's interesting. There's more going on. There's also recurrent processing going on. But I think that's not fair because we don't put these 2 conditions on equal footing. Besides that, so that's a performance confound. You're usually better in general in attention tasks than in masking tasks on average. They are, to my knowledge, very rarely directly compared in a single experiment with the same stimuli, same techniques, etc. And I'm also not a big fan of post hoc sorting of trials that you don't see in general. And we have some papers out there where we make these ideas more explicit. So I'd like to keep I like to stick to the manipulations and not use post hoc sorting. So another difficulty I think is so far it's very difficult to separate feed forward and recurrent processing because many studies are not really designed to do that in a way that the original studies by Victor Lammert and his colleagues were really designed to separate feed forward and feedback because you could measure those like V1 neurons and we know they like orientations, etc. But many studies in humans, they don't. And I know you can do layers, for example, in fMRI, etc. But it wasn't really satisfying to me, at least for the goals that we had. So we designed a new stimulus set that we believe can do that. And then we use causal manipulations using NMDA blockers, and I will tell you later why, to get a deeper insight about the link between conscious states and conscious content. This will come later. So what do we do? So these are two papers that I'm going to explain, all pioneered or spearheaded by Samuel Norman. He was a PhD student in the lab. And first paper, we established the possibility of separating these different types of neural processing in humans and relate these to attentional and perceptual impairments. And the second paper, we explore the underlying causal mechanisms involved, not causal, but causal. So what we do is that we designed a stimulus set that we believe is able to separate feed-forward, horizontal, and feedback connections. And it's all based on previous work using the Ganesha illusion. So this is the Ganesha illusion here on the left. And the idea is when you look at this thing, that what you actually see is sort of a triangle lying on top of these Pac-Mans, right? It sort of pops out in a way. It's brighter. It has these phenomenal properties that that are really specific to the Ganesha illusion. And there are many studies out there, and here are just two of them in mice that show that to experience the Ganesha illusion, you need feedback. Okay, so that's the crucial assumption. It's based on many other papers in animals, but also in humans. For example, I saw Peter Kok was joining. He did also layer-specific studies, for example, in fMRI, showing the same ideas that feedback is crucial for perceiving the Ganesha illusion. So we created a stimulus set, which is a 2 by 2 by 2 dimensional space. And I'm going to go over it a bit slow because it's a bit of a twister, and you have to understand it at some point. And then because I'm going to use it more. So there's three factors, three dimensions, 2 by 2 by 2. There is a Ganesha, so the triangle, Ganesha triangle or not. So for example, here in the bottom, you see that there is this Ganesha triangle in both, but in the top, there's not, right? So there is a Ganesha triangle or not. If you do a contrast between the 4 stimuli, there are 8 stimuli, 2 by 2 by 2, the 4 stimuli that have a Ganesha triangle, and you contrast them with the 4 stimuli that don't have a Ganesha triangle, we argue that we isolate recurrent processing because we know from previous work that that's the case. Then there is another interesting feature of these stimuli is that they have this other triangle. So these white two-legged white circles, we call them, which is not the best word, but that's how we call them, create a sort of amodal triangle. So it's not really perceptual. It's more like a cognitive triangle that you can infer that's there. It's not as direct and phenomenal as the Ganesha. And if you can contrast this with the ones that don't have that, we believe that you mostly separate lateral processing. It's all mostly, it's not uniquely, it's EEG, etc. It's not, I'm not going to claim we isolate this, but primarily we will find processing related to lateral processing because we know that lateral processing does these things, right? With these collinear lines that you see here, they are connected in the visual system to lateral connections, etc. And then there is this other contrast that we'll show you, is which when the whole stimulus, or at least the black parts of the stimulus, is rotated either upwards or downwards. So here on the top, you see this one has the Pac-Mans with 1 down, 2 up, right? So and here it has 1 up, 2 down. So most of the contrast, so the energy on the screen is higher in the left for the left stimulus on the top and for the right stimulus on the bottom. So it has a very strong difference in the contrast on the screen. And you'll see if you do EEG decoding, that gives you a massive peak at 80 milliseconds directly after stimulus presentation, reflecting initial feed-forward processing. So there's 2 by 2 by 2. It's always 8. I just highlight here 2, but in fact, it's always 4 stimuli that are in this condition, right? And 4 stimulus that are in that condition, and you collapse across all these other features. So you average out the other features in those cases. Okay, good. This I've just said. So it's a very complicated study, so I go very slow. So then we want to get this idea that we put these two manipulations, namely attentional blink and masking, at equal footing. So what we do, we combine in this study masking and the attentional blink in one block. So we have long lags and short lags of a certain stimulus, and we have strong masking and weak masking. And what we try to do is, for the attentional blink, you know that for short lags like this, you miss the stimulus very often. For long lags, you don't. What we do is we measure the attentional blink on these short lags within a block, and then we adapt a staircase procedure to which is we we adapt the masking strength to in another condition in such a way that it matches, that the performance of the subject will be matched with this condition, the attentional blink, and the masking condition. It will become more clear in the next slide when I show the paradigm. But the idea is you have an attentional blink. Let's say you miss 70, or you see 70% of the stimuli with that lag. Then we create a masking condition where you also see 70% of the stimulus, or in other words, your performance is 70% in both cases, attentional blink and masking. So it's a 2x2 experimental design with two lags, short, long, two masking strengths, weak, strong. So we don't use trial selection. We take all trials in these conditions and we directly compare them. Okay, so here it is. In red, you see the distractors. In black, you see the targets. There's one target, there's a second target, T1, T2, the typical attentional blink. Subjects say, first about the T2, was there an illusion, or in other words, was there this Ganesha triangle or not? So that's the task relevant feature. Is there an illusion or not? Was there an illusion or not? And also they give a confidence level in the same response, whether they're how sure they were. So they get 6 response buttons. The right hand says yes, the left hand says no, and then within those hands we have three different responses, right? You know, you have a confidence response as well as a discrimination response in one. And then they also have to do that for the T1. So you get 2 responses. Then there is here on the top, you see it's a 2x2 experimental design. So it's all about the second stimulus, the T2. The T2 can be presented at the short lag or at the long lag. Short lag is the attentional blink. Long lag, you see it very well. And it can be masked here by these weird thingies after it, strongly or weakly. Right? If it's weakly masked, you see it very well. If it's strongly masked, then we're going to match it to the attentional blink size. So if you compare the 2x2 experimental design, is exactly following this 2x2 matrix by Stan de Haan, right? It's exactly that. And we are comparing these 2 boxes here on the top right, where you have the masked condition on the long lag with the attentional blink on the short lag, but not masked, right? So the attentional blink, not masked, non-attentional blink, masked. Make sure that performance is exactly the same, and then look at feed forward, recurrent, etc. processing in these 4 conditions. Okay, so this is the behavior. It's expressed in AUC, but you can just see it is just because we want to directly compare it to the decoding analysis that we do in the EEG, which are expressed in AUC, but you can just think of it as performance. So if you look at perceptual performance, it basically just means like how good are about saying whether there was a Ganesha or not. So if there's no manipulation, which is this data point, so there's no manipulation, it's not in the attentional blink, it's this one. It's a long lag, it's unmasked, it's very easy, so you're very good. If you have both manipulations, so it's masked and it's in the attentional blink, you're very bad. Okay, that's easy. But this is the crucial comparison in which we were able to match those trials very well. It's very, very, very non-significant. It's not like bordering any significance or anything. It's just very, very, very much the same. So that worked. If you look at metacognitive performance, which is then based on the confidence responses, is actually also interesting. We also match that. For those who are aware of the literature, there was this paper by Ryota Kanai and colleagues at some point where they say that attentional manipulations, you have usually higher metacognition, um, despite equal objective performance, but we weren't able to replicate that. Just saying. So we've now matched those two conditions, and we're going to look at the EEG and see what happens. So we train a classifier on the features of the first stimulus. So it's an independent, in that sense, independent, but a condition that subject also have to access. And we test because, and this has many trials, right? It doesn't have all these conditions, this 2x2. It just, every trial has a T1. We train it on that. We have thousands of trials per subject to train the classifier on the T1. And we test it on the features of the T2.
Simone, can I just ask a quick
Yes.
question? Otherwise, I'll forget because
No,
you
no,
flagged
that's,
the Kanai paper. As far as I remember, I think they had a specific effect on metacognition of when you say no, there's nothing presented. So
yeah, the
did you look at
subjective
the
discriminability of invisibility.
exactly?
Yeah,
Did you split?
we did that.
Yeah.
Yeah, it's in the supplements. It doesn't
Okay.
matter. Yeah,
Okay. All
yeah.
right. Thanks.
Yeah, but good point. I went over it a bit quick. Um, yeah, so we're mostly interested in these two conditions, right? They're completely matched for objective performance, for let's say subjective or at least a second order performance. What happens in the brain? So here you see the first contrast that we do. It says here local contrast decoding. So that means that's this upper right contrast, which we believe reflects feed-forward processing. So it's the contrast on the relative contrast in the upper or lower visual field. And as you see in this early response, it peaks in about 85-ish milliseconds. It's very strong, and it's very independent, or let's say very little dependent on the manipulations that you do here. All these four lines, these conditions that we have, if you look at the peak of this thing, are very similar, right? So it's a very typical feed-forward type profile of responding. So we say feed-forward processing is not affected by any manipulation. Then we look at the other contrast. I'm not going to talk about lateral processing for now, just for the ease of understanding, but I will do later. So I'll just focus on a contrast, Ganesha triangle versus no Ganesha triangle, which reflects recurrent processing. And we find two peaks that we expected based on a previous paper by Johannes Varenvoort. And that's a peak here around 250 or 200 to 250, illustrated here in the topographical map, and one later illustrated here, let's say around 400-ish. So these are the two decoding diagonal. This is diagonal decoding, right, of the classifier responses. And maybe first look at this, the third one, basically this one, the late decoding one. If I put up the behavior, so I put here the behavior on the same scale, so perceptual performance and metacognition. This is just what I've shown you before. It's the same data, just behavior. It mimics very strongly the late peak, right? This one. So the late peak that we see here that reflects recurrent process, we believe reflects conscious access because it's a one-to-one map to the behavior. It's just global ignition type of phenomenon that is just a reflection of the behavior. But the interesting one is this second peak. So here, illusory triangle decoding, 0.2, where the behavior is matched, which was the goal of the study, but the processing is very different, and that basically the blue condition is much higher than the red condition. The blue is the attentional blink, the red is the mass condition. So the reasoning goes like this. This contrast isolates recurrent processing because we compare Ganesha versus no Ganesha, and that is much more spared during inattention, during the attentional blink, than during masking, but only in this earlier window, right? So if you go back to the theories, I would argue this is the feed-forward sweep. This thing is these local recurrent interactions, and the later thing is conscious access, which is sort of one-to-one map to behavior. Why is this? Why is the second one this pre-conscious state? If you go back to the theory, sorry, I should have put another figure. This is this, right, where you have recurrent interactions in the inattention condition, but you do not have them in the mass condition. So that's what you see there. So I know this is very taxing on cognition, I guess, this whole story. But let's say masking leaves the feed-forward sweep intact, and there's ideas about how that works, what masking interrupts with feedback. Perceptual integration, which we test with the Ganesh illusion, is spared during inattention, and global feedback is directly linked to behavior and conscious access. Good. So I think the model is right, and now tested, I think, in a very sort of way that we can actually say the model is right because we put the conditions on the right equal footing. We didn't use post-hoc sorting. We use measures that we believe are able to isolate these different neural processing types. And now we can use that as a starting point to do pharmacological manipulations. I say the stimulus are right just for these kinds of simple one stimulus type of presentations. I don't think we should look at like for awareness like this if you think about real sort of the stream of consciousness and try to ask questions about when are we seeing the first initiation of recurrent processing, and that is where the magic happens, etc. I don't think that's the right type of questions that we should address, because I think in real life, when you think about the stream of consciousness, you have basically all the time this conscious state. All the time your brain is processing like stimuli, integrate them like from previous times. And every time a new feed forward sweep comes in and sort of integrates with that mush of stuff that's already going on. And it doesn't make any sense to say when did it start and when did it end. And I'm happy to talk about that later, but that's just for me to sort of flag that out here. So I'd like to go back to the original figure. I know I look at the time, I think I need about 10 more minutes, Steve. Is that okay?
That's totally fine. Yeah.
Yeah. So now we want to try a deeper link between these levels of consciousness and these states of consciousness. And when we tried to find this deeper link, if you look at the type of anesthetics that are used in the hospitals to put people under anesthesia, many of them relate to GABA, they increase GABA, or they are NMDA antagonists. So for example, ketamine is a very strong NMDA antagonist, and things like propofol are very strong GABAergic enhancers. So what we thought is okay, and if you look at papers that try to link perception to these different neurotransmitters, and there's one, for example, this study that used these same stimuli that I've just illustrated in the beginning. You see that the idea is that AMPA receptors, so it's both glutamatergic responses, that AMPA receptors carry the feed-forward sweep, and NMDA receptors carry feedback activity. Why is that? Is it because for an NMDA receptor to become activated, you first need to activate the cell. Then there is a magnesium block, which is sitting on the NMDA receptor, which is removed, and then you can activate that NMDA receptor. So the cell has to be activated first by the feed-forward sweep for it to be receptive to feedback. That's the idea. So what we did is we didn't want to use ketamine because of its very strong hallucinative properties, and it's very difficult to double-blind things, etc., because people just know that they're taking ketamine, etc. So we picked another pharmacological agent, which is memantine, or memantine, I think. So it's an NMDA blocker. It's used for Alzheimer's, and it has the same properties, or it has similar properties, let's say that, as ketamine, in the sense that it's an NMDA blocker, without all these, hallucinative effects. People basically don't know they're taking it. So the idea is very simple. You take memantine, you put people in the EEG or in the fMRI. We did both. I'm not going to talk about the fMRI. And we look at the same type of stimuli and tasks that I've introduced you. It took quite long to introduce, but then see what happens with these different types of processes that I've just illustrated. So just a reminder, it's the exact same type of stimuli, the same type of contrast. In the first study, it's also an attentional blink and a masking experiment, but I won't talk about these things. I will just talk about simpler contrasts for the ease of understanding. So here is the response that you see to a single stimulus, and this is the T1 response from the previous type of design. This is just the T1 response. So it's a stimulus that is very clear. You can see it. You can do very good decoding, etc. And you just see the local contrast and the illusion contrast that I've shown you before. And now we also do the collinearity contrast, which is this middle one that I didn't show you in the previous study. The decoding looks slightly different because this is off-diagonal decoding. For those who know. For those who don't, doesn't matter. But it's a slightly different type of signal that we look at, and I will explain you later why. So basically, what you see is the local contrast. Same thing happens. You have this very early peak, but it's not affected by memantine. Same for the collinearity decoding. But for the illusion decoding, we have a very strong effect. Funnily enough, it's in the wrong direction. So it means decoding of the Ganesha increases when you get memantine. So when you block NMDA, at least that's what we thought, you get increased decoding of the Ganesha illusion. So it's very specific. It's not messing up with feed forward. It's not messing up with local or with lateral connection. It messes up with the illusion, which we expected, but in the wrong way. So then we were like, okay, wait, this is annoying. It's nice that it's selective, but it's annoying that it's different. Is this just a fluke? We measured 30 subjects. It was like a lot of work, full day sessions with drugs. It said, you know the drill. Okay, at least in this experiment, we were able to look at the T2 decoding. So this is T1. We look at T2 decoding. That's here on the left. It's the same experiment, different stimulus. But we also see, so here we look at the Ganesha decoding, basically this one that I showed you on the right, but now for T2, we find the same thing. We're like, okay, wait, let's just do an entirely new experiment, new subjects, 30 subjects again memantine, again placebo, because yeah, it's just weird. We find exactly the same thing. So it's very clear, memantine as an NMDA blocker directly interferes only with Ganesha decoding, aka recurrent processing. In behavior, we didn't find much because it was a very subtle manipulation. So we are now doing studies actually trying to use studies using ketamine because yeah, okay, we still want to see is there something specific about the complicated actions of memantine that it increases and not decreases. So we're using ketamine for future studies. Um, I'll just give you a bit of flavors of two other things that are without explaining the details, because now I've explained many details, which you may find interesting. And that's we also with these memantine studies, we had an expectation type of manipulation where we know that expectations change your perception, right? If you see either ABC or you see 12, 13, 14, so there's many contextual effects on perception. And what we did in one of these studies, we gave people also memantine and placebo. I'm showing you again feed forward decoding and recurrent processing decoding. Feed forward on the top, here on the top, illusion decoding on the bottom. But now what we did is we did a base rate manipulation. So base rate manipulation is we have more, for example, target present trials in one block as compared to target absent. So for example, subjects expect to see many Ganesha stimuli. So we like 75% of the trials in a block has a Ganesha stimulus and 25% doesn't have a Ganesha stimulus. And we do the same thing for the local contrast. So 75% of the trials is rotated upwards and 25 is rotated downwards. So subjects over the course of the experiment build up expectations about what is the likely stimulus that will be presented. And as you see here, is that on the top, the feed forward decoding, expected and unexpected. And here you see the peak. It is not affected by expectations. So there's no feed forward driven modulation of these base rate manipulations. If you look at the illusion decoding, it's again memantine and placebo. We still find the drug effect again, so it's the same thing. It's actually one of the two studies that I just presented, so that's clear. There's a clear expectation effect. So unexpected Ganeshas are decoded much better than expected, which is pretty common in these base rate type of manipulation. It's like an oddball effect. But there's no effect of memantine on predictions. So the idea is a bit, okay, all feedback is alike, something like that. Is yeah, you manipulate NMDA receptors, you get you mess up with feedback. It's not like that. An NMDA receptor blocking, at least in this case, affects the priors that you have about like Ganesha type of illusions, perceptual inferences about that, but not related to these very short-lived, task-dependent manipulations that you do in these kinds of experiments. We can chat about this in the questions later. So that's one thing, and then I think I'll stop. I have one more thing, but I think this is a bit too complicated to do as well. So I would just say that feedback is crucial for conscious experience and feed forward is not. Feedback is relatively spared by inattention, but not by masking, even when performance is matched, right? So the models, these 2x2 models seem right in that respect. But then we also see that feedback is at least partly NMDA mediated, although I have to say we don't really clearly know how exactly, so we're still working on that question. Not all feedback is alike. For example, things like memantine does not affect short-term expectations about stimulus likelihood. And there's still also many unknowns about the link between arousal and recurrency or conscious perception. So also like really trying to now link the first part of the talk, which I didn't talk about much, but this inverted U relationship between arousal and perception. How does that relate to recurrency or feed-forward processing, etc.? Which of these signals would also show you this inverted U shape? And I think for true understanding of perceptual experience, we need to move away from these single stimulus models. And I think my guess is that we probably end up with some neural version of multiple draft theory where you have, yeah, let's chat about that later. So thanks for having me, and I'm happy to take questions.
Brilliant. Thank